Magnificenzen, spectabiles, dear guests of honor, dear colleagues, ladies and gentlemen, dear guests who are joining us via our media partner Valiant Zeitung. We would like to welcome you to the opening event of our new center here at TU Wien, the Center for Artificial Intelligence and Machine Learning, or CAML in short. My name is Clemens Heitzinger, and together with my colleague Stefan Woltran, I will guide you through today's exciting afternoon. We are here in TU Wien's Kuppelsaal, which provides the festive surroundings. Unfortunately, it is nearly empty today, as this is an online-only event. However, we will provide a recording of today's event later on our website. Let's have a look at the program. Stefan, please.
Okay, good afternoon, also from my side. So what have we planned for today? So first of all, we will have welcome addresses from our rector and from the two deans which are involved, of the faculties involved in this center. Then we immediately move on to the keynote talk, where we are, of course, very honored to have Leslie Valiant today with us, Turing Award winner, who will talk about how to augment supervised learning with reasoning. Then, depending on how long the Q&A session is, we will have a short break, but continue after that with a brief and compact presentation of the center, what we plan, who we are. And afterwards, we will have a panel discussion where we want to shed light on AI in the, so to say, in between academic research on the one hand and societal impact on the other hand. And here we have four renowned experts which we have here for the discussion. And around 7 p.m., we will have some short closing remarks. Okay, but without further ado, I would now welcome our speakers for the welcome addresses, and we start with our rector, Sabine Seidler. Thank you very much for being here.
Oh, thank you. Distinguished guests, dear colleagues, it's my great pleasure to officially open the Center for Artificial Intelligence and Machine Learning here today in our Cupola Hall, our Kuppelsaal. We have had to wait a long time for this moment, and unfortunately, the pandemic is still playing a major role. That's why I am particularly blessed that you have decided against all odds to make this opening today. This Interfaculty Collaboration Center has everything that we strategically expect from such a collaboration center. Excellent scientists from research groups in the Faculty of Computer Science and the Faculty of Mathematics and Geoinformation are joining forces to position TU Wien as an Austrian Center for Excellence for Artificial Intelligence and Machine Learning, both in the fundamentals and in the application. The three thematic areas to be worked on at the center are artificial intelligence and machine learning methods, and explainable AI and AI aspects in digital humanism are not already internationally visible, but AI aspects in digital humanism, a national and international USB. Not least because they are represented by excellent scientists at TU Wien. Among them are bodies from the ERC, Wittgenstein and START grants, and even CD Lab directors. The breadth of the grants alone shows that this desired value creation can be covered from the basis to the application. The instrument TU Collaboration Center, in the long title, TU Internal Collaborative Interdisciplinary Research Projects, was launched in 2002, at a time when interfaculty work was rather than the exception. Today, fortunately, this has changed. During this time, the comparatively low three-shot founding instrument has proven itself extraordinarily well, not only resulting in various national and international activities of the centers, such as publications, colloquia, workshops, conferences, summer schools, and so on, but also in extraordinarily successful project applications ranging from doctoral colleges to special research programs of the FWF. As you can see, the expectations for the team of the Center for Artificial Intelligence and Machine Learning are high. I'm sure you will fulfill them. Where are the guys? Yeah, okay. And I wish you successful collaborative work.
Dear ladies and gentlemen, here at TU Wien and out there in our virtual world. The Faculty of Informatics of TU Wien has a long-lasting scholarly and scientific relationship with AI research. Already in 1987, the research unit Databases and Artificial Intelligence, DBAI for short, has been established by Georg Gottlob. Ever since, zillions of students and scientists have been trained in facts and rules, implicit knowledge and explicit knowledge, data, their relationship in their interpretation. The research unit DBAI defied all AI winters and became one of the most important world-renowned logic-based AI research groups. But AI is not AI, as we have learned. On the one hand, there is the AI we have known for more than 40 years at TU Wien, which is the so-called rule-based symbolic AI, the logic-based AI. But there's another one, the subsymbolic, the data-based AI, which is also known machine learning. Machine learning is mainly kind of influenced by biology-inspired neural networks and by huge amounts of data, so-called big data. Both areas of AI, both the symbolic and the subsymbolic one, are prominent represented at TU Wien, both at the Faculty of Informatics and at the Faculty of Mathematics and Geoinformation. Therefore, I'm very happy and very pleased that we could establish, together with the Rectorate, this newly created Center for Artificial Intelligence and Machine Learning. But now I have mainly told about history. We know when we now open any kind of newspaper, be it more scientifically or be it just a daily one, AI is everywhere. On each paper we read, AI is responsible for ABC. I want to provide one quote, which is more than 70 years ago. The representation of the world, like the world itself, is a work of man, I would call mankind. They describe it from their point of view, which they mistake for the absolute truth. I don't know if you remember, it is Simone de Beauvoir, Das andere Geschlecht, Le Deuxième Sexe, where she describes the situation that we make our reality and we kind of mistake it for what is real. And I think this is what I would like to have is this new Center for AI and Machine Learning. Develop, based on your scientific excellence, develop new tools, techniques, and methodologies for industry, for policymakers, for the society, for a better world. Thank you.
So can I already start, or do you announce me first? Okay, I think I can start. So my name is Wolfgang Wagner. I'm the Dean of Faculty for Mathematics and Geoinformation. It's also my big pleasure to speak a few opening words on the occasion of the opening of the center. At our faculty, we do a lot of basic and applied research in machine learning and artificial intelligence. And when questioning and talking with colleagues from our faculty, what they're doing, it's really amazing how the diversity of work that is going on in our faculty. Myself, I'm a scientist in Earth observation, and we've been mostly using machine learning techniques for understanding big Earth observation data sets and the relationship, for example, with climate data. So, and what has in the past been like the standard tools in like statistical methods like correlation and regression analysis, nowadays in our discipline, we are using machine learning techniques basically almost in every second paper, I would say. And in fact, the results are often very good and astoundingly good. But there's also some buts. Like one of the buts is that it's really often difficult to understand why the results are as good as they are. And sometimes we observe that results are good, but for wrong physical reasons. That brings me to the second but. We often have troubles in transferring the results to other applications or to other regions. So it's not, we need to have a better understanding how the methods are working and how they can be transferred and to make them more robust. And finally, and last but not least, is that we also observe that the methods are often only working if the data sets that we are using are really very good. Yeah, so if you don't have an excellent database, you can try different machine learning techniques, but all of them fail. So I think that brings me to a very important aspect that is close to my heart, is that I hope that the center will also engage in practical aspects, for example, on data stewardship and actually bringing the machine learning techniques and artificial intelligence methods to the data, also deploying it, for example, on GPU clusters. So you see, I think there's lots of work coming up to the center. So there's lots of basic questions we need to address, and I wish the center all the best for its work. Thank you very much.
Thank you all very much for your welcome addresses. It's highly appreciated. And we'll now continue with our keynote talk. It's a great honor and pleasure to have such a distinguished keynote speaker here with us today. His work has been fundamental to theoretical computer science, and he's having a truly remarkable career. He was born close to here in Budapest. He was educated at King's College, Cambridge, Imperial College London, and at Warwick University, where he received his PhD in 1974. He taught at Carnegie Mellon University, Leeds University, and the University of Edinburgh. He is currently T. Jefferson Coolidge Professor of Computer Science and Applied Mathematics in the School of Engineering and Applied Sciences at Harvard University, where he has taught since 1982. His work has ranged over complexity theory, learning, artificial intelligence, computational neuroscience, and evolution. He's the author of 2 books, Circuits of the Mind and Probably Approximately Correct. In his 2013 book, Probably Approximately Correct, he investigates the connections between learning and evolution, pointing out that quantitative understanding is necessary. Among his many honors are the Nowotny Prize at the International Congress of Mathematicians in 1986, the Newt Award in 1997, and the European Association for Theoretical Computer Science Award in 2008, and the 2010 EM Turing Award. He's a fellow of the British Society and a member of the US National Academy of Sciences. His keynote talk, How to Augment Supervised Learning with Reasoning, fits very well into the mission of our center, as it is about joining different approaches to address the broader goals of AI. If you in the audience have any questions, please post them in the chat. Now, please join us in welcoming Professor Leslie Valiant.
So hello, I hope you can all hear me. So thank you very much for inviting me to this occasion. So it's a pleasure to be here, and congratulations to all of you for opening your Center for AI and Machine Learning. This is a difficult time for everyone around the world, but I'm sure it's a good time to open a center in machine learning and AI. I've worked in various aspects of computer science, and there's certainly something unique about this area of machine learning and AI. So in some sense, it's very intrusive into the human mind. And it, as I think Alan Turing said a long time ago, one justification of working in AI is that it'll help us find out more about ourselves. So what I'll describe mainly my own approach to how we should go forward. But very briefly, it's an approach which tries to unify the two main threads which have already been discussed, which is rule-based AI and machine learning. First, I'll remind you of one or two aspects of the history of AI, which many of you will be familiar. And let's see whether I can share my screen. Okay, so I hope you can see my screen. I just want to cover three aspects of the history of AI as background. So maybe the first work which is very specifically about AI is a paper by Alan Turing, which was unpublished written in 1948. But this was based on this was the basis of his more famous paper published in Mind, which defined the Turing test. So basically, he was asking the very basic question that what can we expect of a machine which has a brain but hasn't got a body? So by this he meant that much of the information we get from the world is by some sort of physical interaction. And if we have just an abstraction of an electronic machine, what kind of things could it do? And so he considered various possible applications of computers. One was game playing like chess, learning languages, translation of languages, cryptography, and mathematics. And his comment was that of these various applications, game playing, number one, and cryptography are very good applications for machines because it's kind of a closed system. The rules of the game of chess are you can put in a machine, and you don't have the problem of machine getting information which may be hard for it to get. And similarly with mathematics. Then he also said that translation of languages are good as well, and also mathematics. And then he said that what would be most impressive is the learning of languages. He didn't explain very well what he meant by this, but I think what he meant is that if you send a robot to a strange country and you expect it to interact with people and learn the language, then that's much more difficult, because the information which the robot would need to have would be a lot of common sense information which we don't know how to get into a computer. So I think this rather brief comment shows an amazing foresight. In some sense, this is where we are in AI. We can do language translation quite well. We can play games pretty well. Cryptography, certainly computers are used for somewhat mathematics. Okay, so just from this very simple criterion that you have to make sure that your computer has access to the information you need. From a basic principle, he showed amazing foresight into describing what our world is like 70 years later. So that's the first bit of history. So then AI did go through an optimistic phase, overly optimistic phase. So this is Herbert Simon 10 years later. And so this was an after-dinner speech he made at a conference, which was also written up as a paper, co-authored with Alan Newell. And so here he made some rather more dangerous predictions of what would happen within 10 years. That this would have had to have happened by 1968. So the first one was that a digital computer will be the world's chess champion within 10 years, unless the rules are barred from competition. So of course, this took much longer. Digital computer will discover and prove an important new mathematical theorem. Well, probably this hasn't quite happened. Digital computer will write music that will be accepted by critics as possessing considerable aesthetic value. Not clear. And one which I think is important, but again hasn't quite happened, is that most theories in psychology will take the form of computer programs or of qualitative statements about the characteristics of computer programs. These are all, in retrospect, very important predictions, but they were over-optimistic. I think one of the conclusions maybe, or one of the comments would be that, so I don't think Alan Turing had very definite ideas of how he would go about doing some of the things like language translation. Or some of the things he pointed out he was an expert on. He was an expert on cryptography, clearly, and also he did write programs for computer chess. So what Alan Newell wanted to base his programming on would be optimization methods, search methods, which he believed in. So these were just an over-optimistic phase of AI. So my background is in kind of algorithms and complexity, and I was looking at AI from afar. But sometime in the 1980s, I think I got interested, and it became clear to me, and I think to some other people at the same time, that somehow learning would have to be the key to AI. It doesn't mean it's everything, but it's somehow the key you use to get in and kind of open up the area. Okay, so I got interested in learning. So the question is, what exactly is learning? What is machine learning, and how do you use it? And these are the big themes which are still being explored. So in the meantime, of course, machine learning has become something very definite in society and in science. It's already been pointed out in the introductory remarks. Maybe just to change, again, I'll just have one kind of extended quote for that. So this is, I suppose, 4 years ago, machine learning had become something widely used in industry, and people realized that this was real and that this would have major implications on jobs. Okay, so this is an article written by someone in a business school and a computer scientist who tried to explain in general terms what's the impact of machine learning on jobs. And so they spelled out which jobs will be replaced by machine learning. And so this is something very definite now, as again has been pointed out in the introductory remarks. So in this formulation, they had 5 requirements which had to be satisfied for a job to be replaceable by a computer. So the first one was that your job involves doing a function, computing something with very well-defined inputs and outputs. Second requirement was that there should be a large data set which generates ideal performance. So if you've got many examples for how to do your job, that's also bad if you want to keep your job as a human. There should be clear defined goals and metrics. So clearly, people should be able to decide what good performance is and what isn't. There should be tolerance for error. In machine learning, inevitably, if it's statistics-based, then errors will be made, and you may try to drive down the error, but you have to be tolerant to error. And the last one was that the function shouldn't change too rapidly with time, which means that what you've learned yesterday should be useful tomorrow. And they're not. So these are some positive requirements for tasks to be reproduced by machine, and they also had 3 negative ones. One was that you shouldn't need reasoning. You shouldn't need long chains of reasoning, which depend on diverse background knowledge or common sense, because these kind of tasks which humans do all the time, machine learning at the moment doesn't do too well. Another requirement was that you do your job, but you shouldn't need to explain it, how you've come to your decisions, because again, machines don't do this too well. And then the last one maybe refers back to Turing's point that if the job should need no special physical dexterity or skills, mobility. That would be some sort of area of robotics, but machine learning directly doesn't answer that. You have to do something extra. So I'm just I've brought up this slide just because it shows how machine learning has come to mean a very definite set of requirements and a very definite set of accomplishments, what machine learning can do. And I think this is useful to know because all the publicity about AI and recent progress and applications do refer to essentially to restrictions which are contained on this slide. So this is something which can be done very well at the moment. So the question is, where do we go from here? And that's what I want to discuss. So this is essentially my thoughts. So I think in machine learning, the interactions between theory and practice are very good. And there's also much need for it because there's much useful practice which doesn't have a good theory, and there's also much good theory which could do with more practice. So there's a big gap. There are some gaps, but there's a good interaction as well. So I'll describe what my worldview is at this point and where one could go forward. So in my view, so with machine learning or AI in general, I suppose there are four different components which are all equally important and you can't separate. So one is that you want to define what you're trying to accomplish. What's the phenomenon? It's probably a cognitive phenomenon. We know that's something which humans do, and you want to be able to emulate by machine. So this is like an input-output requirement. It's not how you do it. So supervised learning is an intuitive notion of learning by examples, which we all have some idea what it means. But you may want to formalize this and say more precisely mathematically what the requirements are. And I'll come back to this later. So packed learning is probably approximately correct learning, which is a formulation of a theoretical formulation of what supervised learning is. But the differences are important, and that will be my main theme. So if you know what you want to accomplish, then you want some good method of accomplishing it. And so you need a learning algorithm. So deep learning is an example of a learning algorithm. But if you're going to do machine learning, then equally important is having a good data set to learn from, or what I call teaching materials. So humans spend an inordinate amount of time preparing teaching materials for schools and universities, and computers will need the same if they learn. So this is a equally important aspect of AI, preparing data, has been mentioned in the introduction. And certainly computing capacity, having a large amount of cheap computing capacity has been a big part of the history of the success of machine learning. And we shouldn't, and all four things are clearly important. Okay, so now I just want to highlight the slightly different criteria one uses in theory and practice, the quite different issues which come up. So supervised learning, learning by examples, is basically what inspires the current successes in machine learning. And when we talk about humans doing supervised learning, we associate with it various common sense capabilities which humans have, which we'd like machines to do. So explainability, already referred to, no spurious correlation. So this means that in the data, you may have some spurious correlation. So maybe a child learning about a certain kind of animal in their book may always find the animal on the left-hand page, but the child won't spuriously think that it's important the animal only occurs on the left-hand page of a book, whereas machines may make some such spurious correlations. So adversarial examples, much discussed, is the idea that you can change some example in ways which are so small that a human doesn't notice it, but the machine can be a trained machine learning classifier may be tricked into misclassifying it. And so lifelong learning is the idea that we can learn bits and pieces of knowledge every day and retain it for a long time. We don't have to be retrained with all the knowledge we have. So these are all obvious things which humans can do. But in fact, machines find these challenging. So now I come to theory. So in theory, you define what more precisely what you want the task you want to accomplish to be, and you don't use just an informal word like supervised learning. So the formulation of supervised learning, which back learning is, formalizes a different aspect of supervised learning, and the aspect is just generalization. So clearly an important aspect of learning by examples is that you want to be able to generalize to new examples. So generalization is the most important thing, and equally important is that you want the process to be computationally realizable. You don't want it to take such a long time that no one can do it. You don't want it to be a purely theoretical exercise. So back learning, which I'll come to in a bit more detail in a second, formalizes efficient training for generalization. And this is what good machine learning algorithms can do. This is what the theory promises. This is what experience guarantees. And then lots of other things which we wish would happen because humans can do it aren't promised and aren't realized, okay, unless you do something different. So what this talk is about is that there's a different direction you can go in, which is to try to bring within the theoretical framework, which is kind of has some guarantees, some different aspect. And so this aspect is to combine the efficient training and generalization with some reasoning, which will be of a similar kind, but not identical to the rule-based AI, which people have done for a long time. And so this I've called robust logic. So this I've been pursuing for quite some time. It's a way of defining a set of tasks to do with learning and reasoning, with some guarantees of accuracy in generalization and reasoning, and also with some guarantees of efficiency. Okay. But very briefly, in more diagrammatic terms, the contrast I want to make between, say, standard machine learning and the way I want it to go is the following: that so SL says supervised learning. So this is a supervised learning box. So the current practice for machine learning is done with a single end-to-end trained box, where you train it on data, and then you test it on data, and that's the end of it. So with robust logic, it will still be based on learning, but as a cartoon, there'll be many supervised learning boxes. You'll train lots of different things. And one way to think about it, for example, is that, say, for each word in an English or German dictionary, you train a recognizer to predict whether that concept is being recognized. So you train on many different concepts. With the idea is that you can use the learned knowledge to reason. You can chain together what you've learned in different boxes in new ways. So this is what reasoning is, that you can you can reach conclusions about rare examples which you haven't encountered before. And this robust logic would have some other things which allow you to reason. But this is the cartoon version of the difference. So with supervised learning, this pack learning gives you a basis for defining what you want as far as efficient generalization. And most basically, what it requires of learning is that as you increase the computational effort, this is the number of computational steps you take, and also the number of examples you take, we'll combine the two. Then the prediction error should go down, and it should go down fast enough. This would be by some fixed power, like 1/√n. It should go down fast enough that you're reasonably rewarded by putting in more and more effort. So the fact that now in machine learning, people may be putting in tens of thousands or hundreds of thousands of dollars worth of electricity into a single training episode shows that it must be rewarding for people to put in such enormous effort into training, because otherwise people wouldn't do it. So if you put in, say, 10 times more effort, you want to be rewarded by, so this would be a constant fraction smaller error. Okay, so this kind of learning, for simple learning algorithms, you can prove that it's got this behavior. So this phenomenon can be shown to be mathematically exist in some reasonably rich environments. And of course, currently heuristics are used for which one cannot prove this, like deep learning, but they still have this, empirically one can show that they have this kind of characteristic. So this is the current practice. So what I'm advocating, robust logic, would be an extension of this, which combines reasoning with supervised learning. And so the main promise of the theory is that, just as in impact learning, you want to control the error. So errors are inevitable, but by making more and more effort, you want to be able to drive down the error. So you want a similar setup where you can control the error by putting in more and more effort. Okay. So that's what I want to talk about. My theme basically is just a single theme. To go back is that compared to the simple scheme, we have to convince ourselves that it's worthwhile to go to this more complicated scheme. Do we really need reasoning? Maybe we don't. And I suppose there are many people currently who are so enthusiastic about deep learning is that they believe that by having a single box learner and making the architecture more and more intricate, we can do everything. So some people do believe that this is the ultimate architecture, but I'll describe an alternative, and the alternative is supported by some theory. But okay, so the question of whether end-to-end supervised learning is enough, which basically is my left-hand diagram of a single box, or whether we need reasoning, is the question I want to address. And I cannot prove to you one way or the other, but one can do a bit of reflection. So if I ask you a question like, did Aristotle like peanuts? Then most people, after a little reflection, will say probably not, because peanuts were not available to him in Greece at that time. So we would use reasoning by putting together different pieces of knowledge we have. Could this be done by a single end-to-end learner? Well, that depends on what data is trained on. But assuming that, supposing we train on data available on the web now, then I don't think there are data sets which describe what Aristotle liked, what foods Aristotle liked. So there's probably no data set from which you can generalize to do this from things on the web. Okay, but this is just a single example, so it's not very convincing. Can one ask this question of whether reasoning is necessary and end-to-end learning versus end-to-end learning? Well, one can do this a bit more systematically and try to test the system whether by adding reasoning you can do better. And the target task which I like is this word completion. And so this essentially is taking a sentence, omitting a word, and challenging the machine or the person to complete the missing word. And this is most interesting, I find interesting on doing it on sentences from newspapers or websites, because they tend to be rather compact. So I sometimes look at websites and try to find some interesting examples. So recently, all the websites are to do with COVID. So I have to take here some examples I got a couple of years ago. And also it's useful to take some examples from somewhere not too familiar. So, okay, so, sorry. So this is something so 3 examples taken from a Vietnamese English language website. Okay, so an example would be, so headline was, struggling shopkeepers at Ho Chi Minh City traditional markets learn to sell. And what's the missing word? And it turned out the missing word was online. Now, was this easy or difficult to solve for a machine learning program, learning from the World Wide Web? And I say that was easy, because if you do searches of sentences which have struggling and shopkeepers and sell, some various combinations, you got a very large number of web pages which had these concepts in, and surely, you know, from all this information, by some sort of pattern matching, you could complete the sentence, or you find a convincing answer. Okay. Now, also on this website, surprisingly, there was stuff on Spanish football. So don't know whether you can solve this if you're interested in Spanish football. The answer was La Liga. But in any case, the point here again is that this was a very easy problem for machine learning program learning from the web, because there were tens of millions of web pages which dealt with the basic concepts of the sentence. So whether you understood the sentence or not, there's so much data out there about this concept that surely this was easy. But the cases where you do need reasoning, apparently, is where there isn't a big data set of existing examples, are where there's something new happens. Okay, so here, Saigon football clubs plan to send players to. So I don't know. So this happened to be Japan. So maybe if you were an expert on football in Asia, you could figure out the most likely country. But certainly, when I looked, this article was already out there, and there were some web pages about this, but all the sentences containing these concepts were about the news which was announced, and possibly before the news, there could have been 0 web pages. So in general, where something new happens, it's a rare event. There's no data set. That's an area where one would think that you do need some reasoning, and computers may still be able to do this as humans can by using previous knowledge we've learned and stringing together these various concepts and reaching a conclusion which isn't directly reachable from your data set. Okay, so this word completion problem is something which you could do in a computer experiment on. Oh, okay, missing word problem. And some years ago, we did with Larus Michael, a graduate student, a very simple experiment on this. Now it would be done very differently. So this was taking sentences from the Wall Street Journal. So we used some simple natural language processing, and we used some simple knowledge graph, WordNet, a dictionary. So we're willing to use knowledge which was known with essential certainty. But the experiment was could we learn rules which express knowledge about the world from these sentences? Okay, so we're learning rules, not rules about the world, with the purpose of stringing these together, reasoning, and predicting the missing word in these sentences. And then we could compare the accuracy of how well we did with the best end-to-end supervised learning methods. So basically, I'm testing the question I asked at the beginning, is a single supervised learning box sufficient to do everything we want to do? Or are there some tasks which we can do better by learning many things about the world and reasoning? So this is a more scientific test of that than just giving you a question like, does Aristotle like peanuts? Okay, so okay, so now I'll okay, so now I'll describe what this robust logic is. Okay, so the method we used for expressing these learned facts about the world and how we learned was the following system, and I'll just describe it briefly. And so this is the technical part of what I think one could try to apply more to solve problems in AI, which at the moment cannot be solved. So very briefly, so this formalizes the mind's eye, which in cognitive terms is the short-term memory. So this is clearly an idea borrowed from cognitive science. And the idea also, which permeates rule-based AI, is that we split the world into many objects and we analyze the relations among them. We've got two objects. One is a dog, and we've got a relationship between the dog and the other object, which is likes. And we want to know, what does the dog like? So the idea is that I wake up in the morning, I've got these tokens in my mind, these blue circles, and I apply various relations and predicates to these tokens, and this is the life of my mind. Okay, and I know that dogs like bones. So in a rule-based system, you'd write this something like this, that if you have a dog and the dog likes something, then it's a bone, okay? Now we won't use rules in the logical sense, but we still want to take advantage of rules. We want all the benefits of rules without paying the price. And we are going to learn these rules. So the rule will be a classifier. Okay, so in fact, the rule, which we'll have now, will be some predictor of whether a token is a bone or not. Okay, so if I say that dog likes something, I may want to predict that it's a bone. So in this robust logic, I will have rules where I'm predicting whether some object in a scene is a bone or not. And the left-hand side will be something which is learned. And it will be learned in with whatever expression my learning algorithm supports. So if deep learning is your favorite method, you use deep learning. Also, if you can afford the computation time, or you could use something much simpler. You could maybe use a perceptron, use some decision tree. So robust logic is neutral to what learning method you use, but you do use it to learn a rule, which is an equivalence. Okay, so the main, so I'll describe robust logic as a series of aspects. And the first aspect is that these rules we're going to learn are equalities. So in machine learning, you learn necessary and sufficient conditions for something to be true. You recognize positive examples, you recognize negative examples, and you want the errors to be small on both sides. The implications in logic don't do that, of course. They're correct in one direction. So the onus on the machine learning version is in some sense much higher, because here I have to not just give one sufficient requirement for predicting a bone, I have to give all sufficient requirements. But this is what machine learning is good at, because that is exactly what machine learning does. So you may think of having rules, again, as I said, where the right-hand side is every possible word in the dictionary, learning a separate rule, and you learn some sort of definition of the word. Okay, so this is the first notion. Second notion, so in this language, which I allow, I will have quantifiers. Inside this expression, I will have quantified expressions in a limited way, but the quantifiers certainly are very local. Well, they exist in X1 really means that there's an object in my scene, one of these tokens with some properties. Okay, so the quantifiers don't refer to the world, they refer to this mind's eye. Okay, so as I said, rules are learned, and what's the domain? What's your data set from which you learn? Well, you learn from the data set is just all the previous experiences of this mind's eye. So the system will analyze everything it sees. So for example, if you learn from natural languages, then every sentence will be analyzed into objects and relations, and you will learn things which are generally true in your experience. There will be a distribution D of typical scenes you will see, and you learn general truths. So if in your experience dogs like bones, then that's what you are going to learn. So in general, supervised and self-supervised, I treat equivalently. So self-supervised means that there's an external supervisor who tells you things, but the scene itself and your previous knowledge gives you enough information to classify things. In this framework, you have these scenes. Some things are specified, some are not specified, and you will learn things from what's specified. Okay. So what is the distribution D? So as I said, these are examples in your mind's eye. It's your experience. And the important thing is that these are now partially specified examples. So this is where a direction in which one parts company with standard machine learning. So the idea is that when we describe the world, so for example, in our mind, supposing we already have some recognizer for every word in a dictionary, then for every word in the dictionary, we have a predicate. But when we see a scene, most of the predicates are not a value isn't given. Okay, so all examples are given with incomplete specifications. So given a scene, we may know that there's a bone there and there's a dog there, but most of the variables are unspecified. But still, we're trying to learn from the world, in this world where things are unspecified, mostly. And of course, the reason why we're able to do this is because the world is very modular. So if you learn about dog eating a bone, there are many other aspects of the scene, like when it took place or where it took place, are not relevant because there's some invariance. The world is modular, and we can learn from partial information. And this is, in some sense, is what makes cognition work. So we know that the amount of information in our working memory, in our mind, is always very small. And miraculously, we can still operate like that. So this robust logic is the same. It always operates with a small amount of information in its mind's eye. It's got a large amount of rules in its long-term memory, but the changing information in its mind's eye is always very small. but somehow the modularity of the world allows us to do this. And consistency. So when one mentions logic, so of course my robust logic is very far from formal logic. My robust logic has got the semantics of machine learning, and hence consistency is not enforced. So we're going to learn all these rules. All the knowledge we have is learned in the machine learning sense. There's some probability of error, but by learning, taking more and more examples, we can drive down the error. Well, there's still always errors, but we walk around with all these rules in our heads, and we never check for consistency. We cannot. So in some cases, we may encounter an example which leads to some sort of contradiction, and we just have to tolerate that. So the system will have lots of rules which are accurate in this probabilistic sense, but it may be that on some very important case, the rules take us to some contradiction which we kind of find intolerable. In that case, we just have to update our rules, our learned rules, and learn it more accurately. Okay, so learning will get us out of inconsistencies which are just intolerable. Okay, so at a high level, this is what the system does. So now going back to this experiment we did, so we implemented the system on the Wall Street Journal data set. And so we tried to predict words. We had these sentences. We took sentences from the Wall Street Journal, which is a business newspaper. Many of the articles were about business, and the words which occurred most frequently were often about business, like price. Okay, so this is a rule which we learned, which predicted whether a missing word was price. Okay, so the idea is you have a sentence, you deleted the word, and you had all these rules which try to predict what the missing word was. And the rest of the sentence you could, of course, see. So this rule said something like, if you got another word X in the sentence, so X, so Y is this missing word, X is a different word, and if this other word really meant the bargain, and the bargain lowered the missing word, then bargains lower price. So that gave some evidence that it was price. Again, competition also lowers the price. So the learning method we used were just linear threshold elements, linear threshold functions. So for example, this 1.09, bigger than 1 meant that the single piece of evidence was sufficient for us to predict that the word was price. Okay, so some other piece of evidence we needed to accumulate, several pieces of some other evidence was conclusive. So much of what these rules learned was kind of nonsense and spurious, but some of it you can interpret in the real world. So when you do this, because you're going to learn very many different boxes, like maybe 10,000 or more for different words, your computing budget for the learning algorithm will go down. So putting in your most expensive learning method like deep learning, you may have to hesitate about because you may not have the computer resources. So you have to do a careful trade-off between computation and how good your learning method is. So in any case, so we did a very naive algorithm, and we found 268 words in the Wall Street Journal, which occurs quite often, and we hoped that we could predict these as missing words. So for these, we learned these rules, and we did do somewhat better than we did with our baseline machine learning method, which we used a similar linear threshold element method for at the time. Okay, so this was an old experiment, but the point of the exercise is that you should use some baseline method. So if you're trying to find out whether something is better than standard end-to-end machine learning, you should apply standard end-to-end machine learning to the problem and then see whether you can do better by doing something else. This is what we tried. And it's a tough competition because the standard end-to-end learning method is somehow statistically very stable, whereas if you do something else, you learn many things, each from a smaller data set. So the number of articles which had priced in was a few sentences, then you introduce various instabilities, and you do get more knowledge, but some becomes less stable. So it's a difficult competition to between doing standard machine learning and doing something else. But I think that's the way to go if you want to do things which you cannot do by standard machine learning at the moment. Okay, so just have two slides which are indicates slight technicalities. So you have a number of objects. These are these tokens, maybe 20. So of course, psychologists tell us that in our mind's eye, we can only keep 7 plus or minus 2 objects in our mind's eye. Here, we have some small moderate number. So what we're trying to predict are like words in English or German, but these words could be relations. So you can learn relations which have multiple arguments. The left-hand side of the rule will be any learnable class you choose, but you have to choose carefully. Now the features will be compound features where you may have some quantifiers. You may be looking for features which are the AND of 2 basic relations. So you may, for example, so we were looking at linear threshold elements on conjunctions of Boolean features. Of course, as you make these compounds more complicated, your number of features explodes. But you know, you can tens of thousands you can easily deal with still, or more. And the learning algorithm, as I said, you choose carefully. And so one thing which we emphasized was attribute efficiency. So the idea is that you may have many features, tens, hundreds of thousands of features, but you expect that only a few of those will be relevant for each rule, and some learning methods are better for that than others. Okay, so so you get some guarantees, but the main guarantee is that when you chain rules together, the chain should be sound. So this is sound in the sense of logic, but not exactly in the same sense. Okay, so what soundness means is that if I've learned 3 rules and I've learned them to a certain accuracy, which my learning method delivered, that when I chain them together, I want some guarantee that the chaining of rules which are accurate separately will be accurate. And so this you can show that if you, even with multiple objects and this and that, in the system, chaining is sound. So we do have a principal basis on which to do reasoning. And so the main difficulty always is the quantitative stuff is tractability. So we have runtimes for these algorithms, error bounds. We want to control the errors, and the various parameters are how many rules we have, rule numbers, how big the rules are, the number of objects in our scene. And it turns out that the runtimes are polynomial. You can make them polynomial in all these things. So for example, the number of objects in your mind's eye, which I said in humans, someone said was 7 plus or minus 2. But fortunately, it turns out that it's not exponential in the 7, it's still polynomial. But the only thing which this scheme doesn't tolerate is having relations of very high arity. So the number of arguments of a relation, if it's 2, 3, 4, the complexity will go up exponentially with that. So you have to divide up your knowledge somehow with relations which have few arguments. And so generally people don't object to that very much. Okay, so this is basically what can be delivered. So when I started, I said that there's various problems people work on to do with machine learning, which are hard to achieve for single box machine learning. And I say that's not surprising because no theory promises it, so you shouldn't expect it. So robust logic, as I said, what it delivers is this reasoning. Just as a comment, I do want to say that this robust logic does change these questions slightly. So I can't answer the questions of explainability, for example, in the terms in which people ask it at the present, but I think it just changes the conversation a little bit. So explainability, I think, is usually used now in the sense that I've got some deep neural network, it makes a recommendation, and you want to know why. Well, maybe that's what you want to do, but what robust logic offers is that it says, well, you shouldn't use a single black box for anything. Instead, you should define what is your vocabulary of discourse. So what are the concepts in which you want to describe the world? Okay, so if you're a bank manager and giving loans, instead of just yes and no and some data, you may also want to predict some aspect of the applicant's life, like whether they have a job or not, or whether they will have a job or not, what their health will be like, which is clearly relevant to the decision. So so the idea here would be, what robust logic would drive you to is to gather more data about the world, to be able to predict more aspects of the world, and then to have a kind of, and to predict more aspects of the world, to have some sort of discussion of what the prediction is. So I would suggest that this is much closer to what humans do. Ultimately, for decisions, if someone asks you, why you chose something, I mean, it's very hard to explain why you make a decision. We all make black box decisions, but we can have a discourse on things related to the decision. So, so the question some children ask, why means, tell me more about it. So with robust logic, you'd be invited to say more about the problem rather than necessarily go inside your deepest black box. And I think the other issues are also robust logic gives a more human interpretation on. So clearly lifelong learning. So clearly we can learn a separate concept every week, and we don't have to relearn what we've learned before. If they're separate boxes, it's just a very naive way in which it's different. And as far as spurious correlations and adversarial examples, so again, I'm not answering the question in the way people want these questions answered, but I'm answering a related question, which is that using robust logic, you would be able to look for multiple confirmations of something. So if you look at something, we're less easily fooled than a machine, because we have multiple ways of confirming whether something looks right. Okay, so this is just a thought. So the proposal I've described as robust logic is a theoretical proposal. So there are arguments for it, so it's clear how you should do it. We do have computing capacity. So the main challenge of showing that it is useful, which it hasn't been shown to be useful on a large scale, is to find some good data sets. So in machine learning, as we know, data sets have been very important in driving the field forward. And we need a good data set for this as well. And so it may be that some more restricted data set would be useful for demonstrating the usefulness of this robust logic. So you need something where you have lots of data and there's some theories to be discovered about the data. So as a default, the one thing one could possibly do is to just do the experiment I mentioned, which was done more than 10 years ago with Larus Michael on just natural language, just using natural language text. So the idea is that we're doing natural language processing. So natural language has all kinds of things you could try to predict about it. And the question is, if we somehow try to learn explicitly facts about the world, rather than just treating sentences in this end-to-end manner, could we do better? Okay, so this framework, packed learning with this robust logic, it does have some promises that, the more effort you make, you can drive down the error. And the question is whether you could demonstrate this for natural language processing in general. So as far as some experimental demonstration, one could do a general natural language processing experiment in the same spirit as the one I described, except do it professionally now with a million times more computing power than we used, which we used a laptop and much more data. Or one could try some different data set, which is somewhere where you've got a large amount of data. But there's some theory to be discovered, which we don't know. Okay, so this is where I'd like to end, and thank you. Thank you.
All right, thank you very much, Leslie. We'll take questions now.
Yes, there was one question during the talk in the context of the word completion problem. And this question is by Richard Vogel, and he was asking whether this word completion problem, whether it would be equally hard for humans too to solve it.
Yes, I think it's you can make it arbitrarily hard for humans. So if you so if you to take these news websites and you delete a word, then so with these examples I showed you, if you show it to a live audience, then usually no one gets it. Okay, with the more difficult ones, no one gets it because there's several possible plausible answers, and I suppose finding the most probable one is difficult. So so I think it would be very challenging for humans as well, because again they would need the right knowledge, yeah, so it is. So I think it's a very good. I think it's a very good AI problem because there's a ground truth. It's a very good AI problem where you could do rigorous experiments. So this is the experiment. This is finished up to be our favorite because there's a ground truth. You can get natural examples, and there's an arbitrary amount of real world knowledge which may be necessary to solve it. So yes, it's hard for humans, yes.
All right, thank you. Another question.
Yes, another question by our colleague Radu Grosso. So he's asking, where do you see the role of reinforcement learning?
So I'm not an expert on reinforcement learning, and I find it difficult to tell the demarcation between supervised learning and reinforcement learning. So the techniques, the algorithms used for reinforcement learning are, of course, now often those which are also used for supervised learning. So I don't know how to make the separation very, very precisely between the two. So I can't answer that question too well, sorry.
All right, thank you. Another question.
Yes, there are questions coming in now.
Okay, great.
So there is another question. So how complicated in matter of parse trees can the sentences be? Putting them into a logical form, predicate logic, is a non-trivial task.
Yes, so yes, so that was one problem with our experiment, that some errors occurred there. So these scenes which we created, that was partly the subject-object structure. We also used linguistic constructs as well. So we can use linguistic constructs. But the idea is that if you, that maybe some of the sentences which are hard to analyze and you make errors on, will introduce noise into the system. So that's one of the trade-offs. So you have to do it well, but the system is able to tolerate, machine learning is able to tolerate noise in the data. But it's an important point, there's this trade-off, yes.
Okay, so there is a question by Philip Lenz, who is asking, so when learning rules, for example, dog likes bone, is there a good way, so when learning rules, is there a good way to abstract rules? So rules not only between dogs and bones, but between animals and other traits?
Well, so in this system, you would kind of, the rules are very complicated, so that we wouldn't dream of analyzing a rule once you've got it. But the idea is that you would have learned rules about animals, you would have learned rules about dogs, and some other relationships among them you would have learned. So if in the data, from the data, you could learn these relations among these different concepts, then you would pick those up. And so we know machine learning is very powerful. So if you've got enough data, then you should be able to abstract much of the information there. But if your question is, do we somehow do anything on the rules, to operate on the rules, to get more out of the rules than what the machine learning algorithm has learned, then the answer is no, I don't know how to do anything else.
Yes, there was a follow-up rule by also Philip Lenz, who asks, and what is a good way to test whether a learner has learned a set of rules? Is instantiation rules with variables sufficient?
Well, here the idea is simply that, as with machine learning, well, the best way of testing whether you've learned the rule is to test it on examples which haven't been used in training, so cross-validation. So if you've got little data, then just looking at the support of the number of examples which you've used to train, somehow you see how many examples you've used to train the rule and see how accurate it was on the training data, give you some indication. Of course, the only valid way is to test it on data which you haven't seen before. So, so everything we do is straight machine learning as far as what the algorithms actually are, is it? So we only judge rules on how good they are at predicting. So, okay, so maybe the word, I'm maybe using the word rule in a misleading sense. But a rule for us is just a classifier, which you've learned, and you judge its usefulness by how well it classifies on unseen examples.
All right, thank you. Do we have more questions?
Yes, there are two more in the chat, but
Two
there's
more?
also one in the audience.
And one in the audience?
Yeah.
So, yeah, let's continue with one from
With
the
one in
chat
the
while
chat,
we
meanwhile.
prepare the microphone.
So, okay, Martin Bublin is asking, what about human AI collaboration? Do we need general AI, if possible at all, or rather an AI that help and extend humans?
Yeah, so on this, okay, so now it's a slightly more philosophical question of what is general AI? In my work, I tend to look at what specific functions you want to realize. I think of cognition. So cognition is obviously a very multifaceted thing, but there are a few important things which you try to isolate and define what they are, like learning and reasoning. So I'm interested in seeing how well you can do these a few basic tasks. So some people by general intelligence mean more like reproducing very accurately what humans do in all aspects. So the latter, I think, is so I'm personally not very highly motivated to reproduce humans in the more general aspects. As far as trying to do science around cognition, I think isolating a few important capabilities we have and trying to do them well by machine is kind of, that's what I'm pursuing. And I think that's still got a long way forward to go. So again, so I'm not quite sure what general intelligence is and whether philosophically it's worth pursuing. I don't know.
All right, I see we have a question in the audience.
There's a question from can you hear me? Yes. There's a question from the audience, Hannes Wertner. First of all, thanks for your excellent presentation. It gave some very basic insights and it was very inspiring. I have two questions. One is a more general one, which is referring to the previous one, which is, do we need explainability? Because when looking at humans, we very often cannot explain why we decide which way. You know the work of Daniel Kahneman with the fast thinking, where we very often implicitly decide. So we ask something more from the machine than we can provide. And the second one is a rather technical one. You showed that you learned better. Your system showed that you learned more or better, but did it also learn faster? Because this is an efficiency argument. What is the cost? What is the price you have to pay to learn those rules besides some facts? Thanks.
Yes. So on the second question, sure. I mean, you have a computer budget. Okay. That's an excellent point. That you're saying that one should compare the same computer budget and two different methods. Okay, so in our experiment, clearly we used more computer power for the second one than the first. But I think in the longer term, there's still the general question of whether one can, in practice, achieve better better predictions using, say, robust logic than end-to-end method. So you have the right formulation. So if you have the fixed computer budget, you should compare the two with the fixed computer budget. We didn't do that, but in exploring this area, one doesn't have to do that all the time. But in the end, you're exactly right. So on explainability, yes, okay. So the example I use on that is that if someone asks you, why you have your umbrella with you, you say because it's going to rain, and why do you mind rain? Because I don't want to get wet. So you've got explanations, but in the end, someone says, why don't you like getting wet? And at some point, as you say, we can't answer anymore. So we give explanations at some higher levels, and if you go low enough, then we don't give explanations either. But I think the robust logic is exactly this kind of thing, that that each, in the end, you will learn each rule as some sort of machine learning box, and maybe you can't go inside to give an explanation for, but you can have a discussion of other things which you found to be true, which you're predicting about the scene. So I think human explainability is a mix. We can explain some things and not other things. And I think this is a reasonable thing to aim for. And I think robust logic reflects that pretty well. But in the most extreme senses in which explainability is sought, I think it does get absurd that, if you have a big neural net which predicts something to as big accuracy as possible, explainability at some point becomes a naive question, I think. Yeah, so I think pushing explainability too far is a mistake, I think, yes.
All right, thank you. I believe we have time for maybe one or two at most questions.
Okay, so there is one about quantum computing. Maybe this is interesting. So will quantum computing change AI and ML from your point of view? What is your take on quantum computing and its impact?
Well, I think practical quantum computing, as far as I can tell, is still a very long way away. So it's, I think it's extremely interesting science. This basics of where quantum theory and computer science meet. I think it's all fascinating, but I don't, from what I see, I don't think it's going to impact practical computing for a very long time. So, okay, so I think it's just very far in the future as far as I can tell.
One quick question.
Yeah, can knowledge be transformed from a rich resource language to a low resource language?
So from a rich resource language?
Yeah, this is how it's there. This is how the question stated is.
From a rich resource language to a low resource language.
Yes.
Okay, so I don't quite understand the question, actually. Yes, I don't know.
So the Giuseppe Attadi, so with the question, so that transformer models are quite good at guessing missing words. Can you comment on that, please?
Yeah. So so there are two ways to go. So if you got so these deep networks which do things very effectively, and clearly it's tempting to change the architecture inside to see how far you can go. So so in some sense, these attention mechanisms may be replicating, change of reasoning, but so somehow I think the replicating reasoning more explicitly is a more natural way of going. So I think clearly you'll be able to do more and more with more advanced neural network architectures. But as far as your comment that these architectures can do missing words well, there's always a question like with the examples I gave. So if the missing word is well supported by the data, then then it's easy to do. If it needs a long chain of reasoning, like if it's some news where you have to careful change of reasoning, then I'd be surprised if any kind of neural net can do well in that. Okay, so I think reasoning is useful when we reason about some case which has never occurred to me before or is very rare, and still somehow we can chain together a piece of knowledge. Yeah, so no one can prove to you ultimately whether this single back book and end-to-end learning will always be preferable to any alternative. So I can't prove it to you either way, but I think this alternative should be explored because from my point of view, it's got a principled quantitative basis for doing reasoning in this way. And so the reason why end-to-end learning works is because that's also got a principled quantitative basis. But I'm just pointing out there's a different direction, which is also principled, which needs to be explored more and could be explored more.
All right, thank you. I think that was a good question to stop here. Let's thank Leslie again for his excellent talk. And also for being available to take so many questions. So we appreciate your time.
Okay, well, thank you for inviting me.
All right, we'll take a short technical break now, about 5 minutes. We need to set up here, and then we'll continue in about 5 minutes with a short presentation of our center and the panel discussion.
Also, direkt
Okay. All right, welcome back, ladies and gentlemen. We'll now continue with a short presentation about the mission of our center. Artificial intelligence and machine learning go back to intelligence and learning, and these are two subjects, intelligence and learning, that have been captivating and inspiring for indeed thousands of years. We can start with Greek mythology, the stories of Prometheus and Epimetheus. So you see here in this painting how Prometheus is bringing fire from Mount Olympus to the humans. And of course, fire here is a metaphor for intelligence. We have the stories of Hephaestus' mechanical helpers, which he created to help him with his hard and dangerous work. We have the stories of golems, which are also kind of artificial intelligences. Going forward, we have Leibniz's imperative calculemus, let's calculate. And he was not only referring to the laws of physics, but also to arguments, to discussions, to statements, let's calculate the truth. And more recently, we have robots that, of course, are supposed to make our lives easier. There are two aspects here. One aspect is we try to understand intelligence. How does it work? What does it mean? Right? So, but at this point in time, we do not understand how the human brain works. We are far away from doing that. A second aspect is how can these artificial intelligences be useful to us, right? So this is the idea that goes back thousands of years. Wouldn't it be great if we had machines that would make our lives easier, that would do the boring, repetitive, hard work for us? And this means there are obviously lots of ramifications and impact from such a work, right? That affects us personally, that affects us economically, right? Those machines and programs have huge economic impact, and they also have huge societal impact. This is why we have this panel discussion later on to go into these questions. Now, today we are starting a new journey. We are embarking on a new journey in our center. So this is a starting point, and it's a good time to reflect where we are coming from and where we are going. Where are we coming from in the field of artificial intelligence? I would like to recall here two personalities, Norbert Wiener and John McCarthy. Norbert Wiener, you can see on the left-hand side, he wrote in 1948 a highly influential book, Cybernetics, or Control and Communication in the Animal and the Machine. He was a mathematician. So he used continuous methods, continuous mathematics, and he was coming from control theory. On the other hand, here on the right-hand side, we have John McCarthy. He was very much behind the term artificial intelligence. He was a logician by training. He invented Lisp, and he used discrete methods. So early on, we see these two very different approaches. We have continuous and discrete methods. We have symbolic and non-symbolic methods. And this is continued throughout the history of AI. Our goal in our center is to unite both approaches, right? So the problems are so hard. We need to bring together people who are experts in various fields and make them work on the hard problems. This is also a theme that we saw in the keynote talk today. Now, going forward a couple of years, if one would be asked what is the date of birth, the place of birth of artificial intelligence, many people would say it's the Dartmouth conference, or precisely the Dartmouth Summer Research Project on Artificial Intelligence. It was organized in summer 1956 by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, all four of whom went on to have distinguished scientific careers. A year before, in 1955, they submitted a proposal to the Rockefeller Foundation requesting $13,500 for the summer research project. And I'm quoting here from the proposal, the emphasis are mine. So they want to work on artificial intelligence based on the conjecture that every aspect of learning or any other feature of intelligence can be, in principle, so precisely described that a machine can be made to simulate it. So here again, we see the desire to understand intelligence, to dissect it, and to build something new out of it, to generate, to create intelligences. They say they believe that significant advance can be made if they have funding for a summer. So it's always good to be optimistic. They were wildly optimistic. And we see here now, this is the starting point of a history of 65 years. We are now here 65 years later. And we see that an interesting history has developed. It's a nonlinear history. It is full of twists and turns. It was found that approaches that seemed to be very valuable were dismissed and problems were solved by completely different methods. So there's a really inspiring history to the subject. It's very nonlinear and really worth remembering. Now, here we are, and it is easy to argue that, if anything, progress is accelerating, because now we face a perfect storm of ever more computational power that we have at our disposal, more memory, more storage, and an ever increasing amount of data that we can use for learning. So if anything, the progress is accelerating. Prime example here is DeepMind's AlphaZero, started in a series of papers around 2017. So now we have an algorithm that can play chess, Go, and more than 50 Atari 2600 games at superhuman level without using any prior knowledge. So these intelligences are becoming more general, and this is really an inspiring milestone. We face still many challenges. We need to devise more algorithms to face these challenges that come out of applications. We need to develop theoretic frameworks for these algorithms to understand why they work, when they work well. Subjects of trustworthiness, reliability are hugely important when human lives are at stake, when we really have to make sure that we can trust the answer that is calculated. Of course, it is desirable to have some explanation of the results. And another big challenge, wide open, is understanding the human brain. So we have lots of stuff to do, lots of work to do. Who will do the work? So first of all, we hope that you will join us in our endeavor, in our journey in this new center. And we are also very happy to have assembled here a team of highly motivated researchers. Stefan and myself, we will serve as co-directors to the center. We have Ivona Brandic, Thomas Eiter, Peter Filzmoser, and Thomas Gärtner. We have Georg Gottlob, Radu Grosso, Ellen Hambury, Nusret Muslio, Julia Neidhardt, and Stefan Scheider. Please forgive me pointing out at one point we did some statistics, so please forgive me pointing out that among those 12 board members in total, we have 1 Wittgenstein Prize, 1 ERC starting grant, 3 start prizes, 1 Emmy Noether Prize, 1 NSF Early Career Award, 2 Christian Doppler Labs, 1 member of the Austrian Academy of Sciences, ÖRW, 2 fellows of the ACM, and 3 fellows of the European Association for AI. We also have an international advisory board. We are very much looking forward to discussions with them. We have Peter Flach from the University of Bristol, president of the European Association for Data Science. We have Roger Garnham from the University of Southern California, former chair of the SIME Activity Group for Uncertainty Quantification. We have Wolfgang Neidl from the Leibniz Universität Hannover, and executive director of the L3S Research Center there. We have Julia Nieder-Rümelin from LMU München, and former federal minister in Germany. We have Daniela Russ from MIT, head of the Computer Science and Artificial Intelligence Laboratory there, one of the birthplaces of AI. And we have Carles Sierra, director of the Artificial Intelligence Research Institute in Barcelona and president of the European Association for AI. To sum it up, what is our scientific program? What is our goals that we try to achieve? So obviously we have AI and machine learning here. We already discussed that the intersection of these 2 approaches is extremely important. We face huge challenges, so we try to bring together people who are experts in the various methods, in the various fields. We want to bring them together to be able to tackle these challenging problems. So this is the intersection where many believe that lots of progress is to be made, will be made. And this is also a theme that we saw in the keynote lecture today. We do take applications seriously. This is a field that has been driven forward by important applications. So we want to work on important applications, take them up, and provide theory algorithms how to solve these problems. And we also hope that our solutions that we propose, our algorithms, our codes, our theory will be helpful, useful to researchers in applications to push their respective fields forward. Last not least, we have digital humanism as the vehicle, as the field where the intersection between technology and society is discussed. We already mentioned in the beginning that those machines would be highly useful for humans, for our personal daily lives, for our economy, and for our society. So this is also something that we keep in mind. Our website is kemel.org. And so much for this presentation of our center, the mission of our center. And we are ready to go to start with the panel discussion. So digital humanism was the perfect keyword, and Stefan, please take it from here.
Right. Thank you, Clemens. So welcome now to this second part of our opening, where we want to take a bit more a general perspective, where we want to reflect on the impact AI has nowadays and in the future, where we want to ask, what does this mean for academia, for universities, how to react on this, and what can centers like ours, but like many others which were launched quite recently, do in this respect. So I'm very happy to have four renowned experts among us here in the Kuppelsaal, Professor Helga Nowotny and Gerhard Friedrich. And in the Zoom I already see, I am very happy to see James Larus and Paul Timmer, so everything worked out. Great to see you. Thank you very much to all of you for being here tonight. I'm looking forward to an exciting discussion. I will introduce the four panelists a bit more in detail during the first round, if you don't mind, and would now start with that. And I will do this first round alphabetically, so therefore Gerhard is already looking at me desperately. So I start with the introduction, and then I put the question for the first round, okay? So Gerhard Friedrich is professor at the University of Klagenfurt in Austria. There he is also Dean of the Faculty of Technical Sciences and directs the Intelligent Business and the Intelligent Systems and Business Informatics Research Group. Previously, he managed the Department for Configuration and Diagnosis Systems at Siemens Austria, so Susan is the industrial background, and was research fellow at Siemens Corporate Research and at the Stanford Research Institute. Gerhard, thanks for being here. And I want to start the discussion maybe with the following statement. So AI has the potential to transform industry and society in a radical way. As a reaction, universities launch centers in order to reflect, bundle, and modernize their activities in terms of research, education, but also outreach. So what would you rate as the most important aspect such an AI center like ours should address?
Okay, yeah, so thank you for this introduction. Thank you for this invitation. I'm very honored. And first, let me congratulate you for establishing such a research center. I think this is really a great thing to do. Well, what is the most important aspect? So this is really very difficult to answer because I mean, usually with such a research center, there are many objectives. Of course, I think one of the main objectives is to do excellent research, I guess. And so starting from basic research, so with basic research, it goes to application-oriented research, and then eventually to new product services and startups. And there, I think you have the chance by doing great research to create the jobs of the future. I think this is very important, a very important task for the society. And I think that the most important part, or most important aspect to do this is to attract bright minds. Yeah, I think this is the key. And in this sense, I would like to cite the Prime Minister of Bavaria. Yeah? He used some very drastic words, but I think there is some truth in this. In the past, there was a military arms race. Today, there is competition for the brightest minds and for technology dominance. And in this sense, I think the most important aspect is to attract bright minds. And as I saw, you already did a great job. And I think this will continue in the future.
Okay, thank you, Gerhard. So now I would like to introduce James Larus, who is in the Zoom. So he's professor and dean of the School of Computer and Communication Science at EPFL in Lausanne, Switzerland. Before that, he was researcher, manager, and director in Microsoft Research for over 16 years and associate professor at the University of Wisconsin. He's ACM fellow since 2006, but what is also very interesting for me and for us is that he's also among the board of directors of the CIS, the Center for Intelligent Systems at EPFL, which maybe has a similar role than we want to have. So James, thanks for being with us. And maybe you can also tell us a little bit about this CIS.
So thank you very much for the invitation. I regret that I'm actually not there. My plans originally were obviously to travel there, but it's difficult these days. CIS stands for Center for Intelligent Systems, which is a center that I established at EPFL along with the collaboration of several other faculties a couple of years back, right before COVID struck. And it's been a very successful center because we had a very clear aim, which is not something that was articulated previously, which I think is actually extremely important for a center of this sort, which is to serve as a congealing point for the people in the university who are interested in using artificial intelligence, machine learning, those techniques, and are interested in learning about this entirely new field and applying it to their own scientific and other endeavors. One of the things that is most striking to me in terms of the scientific field and academia is the explosion of uses of techniques from AI and machine learning in other fields beyond computer science, beyond what you see being done industrially. If you look in physics, if you look in material science, if you look in life sciences, people in all of these fields are coming up with these incredible uses of these techniques and coming up with sort of very unexpected and very, very useful and perhaps even fundamental results that couldn't have been done in other ways. But the expertise is not there. We have a faculty full of people that were educated and trained before these techniques became widespread. They don't have the expertise. So a center like this or center like yours can serve as a point where the university can come together and the techniques and collaborations can be shared across the university so that there can be progress in many, many fields. And this is what CIS has been at EPFL. It's been a place for people who are interested in machine learning and interested in artificial intelligence to come together, to meet each other, to talk about the problems, and to start collaborations. And sort of the collaborations then lead to all of the other good things. They lead to good research, they lead to funding, they lead to proposals, all the things that you need to make a successful center. But really the sort of focus was originally outward, but outward within the university. And of course, more recently, we've gone out of the university and started talking to industry in Switzerland and around us, because that's the natural thing to do with a center at a university. But I think that if you start there, you overlook the opportunity to work with your colleagues on the faculty, and you overlook the opportunity to find some incredibly interesting applications of the techniques. So I'll stop there.
Thank you. So I now continue, and it's my great pleasure to introduce Professor Helga Nowotny now, who is with us in the Kuppelsaal. So she's Professor Emerita of Science and Technology Studies of ETH Zurich and former president of the European Research Council. She's also a member of the Austrian Council for Research and Technology Development, and she received numerous awards, which I only want to mention one very prestigious one, namely the gold medal of the Academia Europaea. Maybe not all of you know this, but she also recently published a book on AI entitled "In AI We Trust: Power, Illusion, and Control of Predictive Algorithms." And I'm also maybe curious to learn a little bit about, say, the European perspective. So what is expected from the universities as stakeholders in this game?
Okay. Thank you. I was struck by the title that you gave for this panel discussion, namely when you spoke about between research and social impact. And I was struck by the connection, because when you speak about social impact, you can think about the impact that you would like to have, but most of the impact is the result of unintended consequences that no one ever thought about. Or as we know, in the beginning, people had very idealistic ideas. When the internet came about, people thought now this will be democratic emancipation, etc., etc. And if we look at the social impact that AI had on society today, it's full of impact. Much of it also negative, I must say. We think of fake news and the speed with which conspiracy theories can circulate without us really having a handle, etc. Apart from the obvious positive ones that were already mentioned. So I thought maybe this should be an entry point to what you could do. And I would like to give you just one example. And this links up to what you said about the European level. As you know, the European Commission is now preparing an AI Act. There's a draft form, the Parliament has still to debate it, etc. It's as always a long process. We know this is how things change at European level. And I thought maybe you could take some of the problems in implementing what this act foresees. For instance, there will most likely be firms have to audit an algorithm. And then comes in the famous explainability. We have heard a lot about it. And of course, you can approach explainability from the theoretical perspective, as we have heard, but you can also ask yourself, what does it mean once you put it into actual practice? And a firm, auditing a firm, of course, means you have to implement what this act foresees. So this might be just one example where you can get engaged and you can start to test it. What actually happens if you start to test it? You find a firm or you find an experimental setup where you start to test what would it actually mean if this European Act on AI is transferred into actual practice, and what are the kind of problems that people will have to cope with. And testing is something we do all the time. So you could provide a service to what happens at European level. You could find a lot of the problems that are unsolved that you may or others may want to dig deeper in the future. So this would be, one concrete example where to get started. I stop here.
Yeah, thank you. So this is already a lot of to-dos for us. So let me, for the moment, introduce our fourth panelists. So I'm very happy to have you here, Paul. So Professor Paul Diemers, he's research associate at the University of Oxford, professor at the European University of Cyprus, and also I have to mention in this term he is also guest professor of the Technical University of Vienna, which we are very happy about. He is board member of the Digital Enlightenment Forum and supervisory board member of the Estonian e-Governance Academy. He has been director at the European Commission dealing with EU legislation and funding for cybersecurity, EIT, digital privacy, digital health, smart cities, e-government, and so on. And he was also cabinet member of the European Commissioner Liikanen and until recently advisor of the European Commission in the Directorate General Sante, which is on digital health. So Paul, thank you very much for joining us today. Yeah, maybe you also can just continue what has been said so far on the different levels.
Yeah, happy to continue, and I hope you hear me well. First of all, continuing on the congratulations, because it's great that you start a center and the whole team behind it at the university. Congratulations, and of course, especially wishing you both, Clemens and Wolfgang, a lot of success in this venture. Of course, for a center like this, you can imagine and have in mind many kind of good things, characteristics like excellence, independence, being productive. But in the title of this panel, like Helga also focused on that, between research and societal impact, I focused actually on the word between. Recently, there was a report made by the Scientific Council that is advising the Dutch government of about 500 pages about AI. And the central word in that is that they say AI is a system technology. And how I interpret it is that AI is kind of like pushing downwards in the stack, you might say, towards data, towards networks, towards the devices, and towards the basic and fundamental technologies, and pushing upwards into users, applications, use cases, people and societies, and actually also countries and global problems to address. And so this kind of sometimes people are saying data is driving the digital economy. Well, it may well soon be that AI is actually the real driver, because that's creating this demand for data and infrastructure and demand and expectation to solve big problems, you know, like problems like that have to do with the climate, that have to do with inequality, pandemics, rare diseases that I've seen, for example, at the European Commission, injustice, and so on. And certainly also these problems of responsible AI. So it's kind of like also there's expectation that you bring things together in between kind of in a technical sense, but also in between in the sense of these various disciplines that we need to have to address these very complex problems. And I've seen myself that that's a huge challenge to bring people together. And I would really wish that the center can be that it can be a place where insights come together, where you can have several perspectives coming together, but also confronting each other, and hopefully ultimately contributing that there is a common language, which is one of the big problems. So you might also phrase it perhaps in a negative sense. I would wish that the center does not become a silo.
Okay, yeah, thank you very much. So that's a lot of say, interesting challenges for us. For the second round, I maybe want to bring in another issue which has not been at least explicitly touched yet, and maybe we this time start with Professor Nowotny and then go through the cycle. And this is the fact that that we have these tech giants nowadays, which not only have taken to some extent the lead in about AI research, but they are also investing a lot in education. They provide online courses. They try to attract students, so to say, as early as possible. So I think this is also to some extent a development where universities kind of have to react. And my question to some extent goes in this direction. Do we need a change in the curricula for computer science? Do we in general and in AI in particular, do we need it maybe also a different access to train our students, that they are aware of their responsibility, or to maybe put it a bit more pathetic? So how can we educate our students such that they use their learned skills not only to make money, but also to make the world a better place?
Yeah, I would like to answer, to take your question and separate it into two parts. The first concerns the kind of competition by big corporations. Now, in this respect, I think Europe is better off than the US, because when I was last time, before the pandemic, visiting the Bay Area, it was so obvious that a public university like the University of California, had a very hard time in keeping their best students, because even before they finished their PhD, they could be hired by some of the big techs for salaries that no public university could compete with. And this means in the end, you undermine the asset that every good university has, namely the training of the future generations. So luckily in Europe, we are not there as yet, I would say, but it is something that in the long term is worrying. How can the universities, if they cannot compete in financial terms with these very attractive offers for the best and brightest graduates they have, how would this happen? Now, the other part of my answer concerns what I consider a major challenge to universities that has become obvious and accelerated through the pandemic. We will not see it next year, but we will see it in the coming years, that the way how the digitalization has been accelerated, and again, many unintended consequences that this has will become apparent in the near future. And this goes far beyond, changing didactics or offering more courses online, or, fine-tuning what we do. The real challenge comes from how can we bring up a curriculum to the 21st century, post-pandemic 21st century. And what I mean by this is the following. Young people during the pandemic, whether they are bright kids in high schools or university students, have discovered that there is a world of knowledge, a space of knowledge out there. And they have access to it by using digital means. And so a bright young person, can go and get this knowledge content for him or for herself, even without having a formal teaching course. But of course, a university or, teachers in general have to integrate this knowledge that these kids bring from wherever and put it into something that is shared, because we still have universities and schools also, because we want to transmit knowledge that is shared by young people as well as their teachers. So I think this is a major challenge, and we have to take the challenge of a curriculum seriously. And what I mean by this is, in Austria, for instance, a curriculum is considered something boring, administrative, that has to be done. There are committees, people fight to keep whatever they did before for 20 years, etc., etc. But really, it is a major epistemological and scientific challenge to come up with a new curriculum, because you have to anticipate the kind of knowledge that will be needed in the future. And of course, there's a lot of uncertainty involved because nobody really knows. But nevertheless, if it's not people like you who else should be able to anticipate this? So I would consider this a really major epistemological and scientific challenge, but also in view of this kind of dispersive effect, again, unintended, that the availability and access to digital content has for many students. And then, they put it together in a kind of do-it-yourself way. It can be very creative, but for the institution, the university, it's a major challenge.
Okay, thank you. Very, very interesting. So, Paul, maybe I try to reshape the question also a bit, because this now comes into my mind. So I'm a bit wondering what we should expect from a computer scientist, from a say PhD student in computer science. Shall we try to make these people more aware? Let me start differently. Shall we put priority to make these people more aware about all these issues which have been mentioned, be it ethical issues, be it other issues, or shall we try to train them better also to talk to other scientists, to other communities? I mean, you have been working in all these interfaces, being e-health, being e-security, e-governance. So what is your experience with computer scientists and when they have to talk to other people?
Let me give an example of what I experienced. So I was responsible for several parts of the Horizon program, and one part was bringing together, you can hear me, hopefully? Yeah. So one part, let me see if I can turn off my microphone a little bit. Is this a bit better?
No, yeah, I think it's a problem here in the room. I think it's not a problem in this. It's more,
okay. Let me, if you don't understand it, tell me. So I was co-responsible for several parts of the Horizon program, the big R&D program, of course. And we had one part that brought together some of these various different backgrounds. It was about international collaboration. It was about modernizing governments. It was about social sciences and humanities. And we had at some moment in time this debate that everybody wanted to do their own thing, of course. And we had only a limited amount of money. And so everybody was fighting for a little part, their own little part. And we said, you are at risk that you make yourselves irrelevant. You need to tackle a real significant problem where precisely you need to have the various insights coming together. And they said, what? Well, this was 2014, and Russia had just invaded Ukraine. So we said, think about our relationships with Russia. That's about war and peace. That's a real problem that we have. And then one voice out of the room said, but you cannot start on that. You first need to know, before you start working on this problem as it is today, you need to understand 2,000 years of history of conflict in the Crimea area. And we said, well, but that's exactly the point. You need to understand from both sides what you're talking about. You need to understand why perhaps modernization of government may not work, because there is 2,000 years of history. And then you need to think creatively about what you could do differently, because we still need to solve the problem, isn't it? What I think was missing at that moment in time was what I alluded to before, and perhaps also Helga mentions that more or less. It's the language on which you can exchange, where you can understand each other, where you can also confront each other, where you can come out of your silo. So I think it's not necessarily for computer scientists to become lawyers, but I think they should understand the language of law. I was just, as a visiting professor, teaching a course on EU digital and policy to people with informatics, sciences background at your university. And I think they can perfectly well, and they showed that they can perfectly well understand what is the reasoning that you have when you are a lawyer. Conversely, it may be quite difficult to make lawyers also understand what is happening in the technical domain. And I think we also need to do bridging there. So I think that's a role that you can fulfill. I would be absolutely in favor of having this type of open discussion and really checking, do people understand each other sufficiently, and also tackling the more fundamental problems of the language, the concepts that we use, the ways we express ourselves. And perhaps indeed we need to look for other kind of languages than the traditional ones, if I use that word in between quotes, the word language.
Thank you very much. So coming back to Gerhard, maybe to the Austrian perspective also, I mean, in contrast to our university, you are the dean at a general university, so there is many different disciplines there. So in answering the question, maybe you can also tell us a little bit about your experience as a computer scientist when joining forces with other people there. Not a good question.
Interesting question. Yeah, in the break we had a discussion with your former team. Yeah, it seems to me that at some point it's very interesting that computer scientists are more interested in humanities and in connection between humanities and computer science, that the core of the humanities are. I don't know why this is the case, but the discussion is very, very difficult, yeah, because these are really complete different worlds of doing research, yeah, and therefore communication is quite difficult, but it could be very fruitful, yeah, and I think we still have to work hard, yeah, to exchange ideas, and I think there are many. Maybe we also should contribute more our ideas to let's say to philosophy, so what we are interested in, yeah, and what we can provide, yeah? Because I think most of them are not aware that there are very close connections. For example, if you look, for example, at logic, yeah, or which I think is very interesting. Well, let's say because there was a lot of discussion now about explainability. So actually, the phenomenon of explainability, I think, is very interesting, and it's actually a cognitive task. Yeah, and I think in order to understand what an explanation is, yeah, it's a very basic question for philosophy and for psychology, and if you really want to understand what explainability is or what explanations are, it's a must, yeah, that you talk with cognitive psychologists, that you talk with philosophers and the whole spectrum of these humanities, yeah. So in this sense, I think it could be very fruitful, but this is, you have to be aware as a computer scientist that you have to open your mind, yeah, because if I look at the papers over the last 30 years on the explanations, they are very, very tiny, yeah, in their aim and scope, yeah, compared to what explainability is in a human sense.
Okay, thank you. Maybe let me stay with you, Gerhard, for 1 minute, because and coming back to the question, which I think is also something I want to ask James. So one aspect in the question was also this competition for the bright students, yes, between industry and academia. And since you and also James, you know both sides, so to say. You have been in industry in relevant positions and in the university. So maybe you also want to comment on this battle between.
Yeah, that's difficult. I mean, I think that the director of ETH said the industry is stealing our students. Yeah, it was a very drastic saying. Yeah, but there is some truth in this. Well, I think it's better to team up. Yeah. So my experience is that the competition, of course, industry wants the brightest minds. I mean, if I had a shortage, yeah, on the bright workforce, yeah, what I'm going to do? I mean, I would invest into courses and education, try to attract the these bright minds. Of course, they do this, and they have a lot of money. I mean, you have to integrate this, for example, these courses somehow in your curricula. I mean, it's free resources. I mean, we should exploit them. Why not? I don't experience this tough competition on the bachelor and master level, but I think so. You mentioned this in especially if you're competing on with respect to PhD students. Yeah, the PhD. If the students got their master degree, they can decide should they go to academia, yeah, or to industry. Okay, and I have to say, unfortunately, many of our bright students we cannot track to the academic world, yeah, for various issues, and I think we have to work also on this, yeah. I mean, of course, but it's not only money, yeah. It's not only money, but it's also the perspective of their career. Yeah, and therefore I think we have to work on this. But on the PhD level, we can team up with the industry, yeah, because there we can work together, yeah. And the industry is very interested now in artificial intelligence. Was not always the case, but now it is, yeah. And I think this gives us the opportunity, if we collaborate with the industry, to attract really bright students and work together with them on interesting topics, which are both interesting for industry but also are interesting for the universities. And I would say that industry is at least in the area of artificial intelligence, industry is also becoming more and more interested into really basic questions and basic research. And this is an opportunity for us.
Okay, thank you. So now, James, do you agree with Gerhard on these aspects? Also, you give me your experience.
No, let me take a contrary opinion. My view is that this is not a real problem. It is a short-term problem. That there is a unmet demand for experts in these new techniques. It's unmet in academia, it's unmet in industry. The best people can go and have a choice of jobs and at fantastic salaries, and that's wonderful. You know, the problem is that many of the best people don't want to go to industry or have been in industry and really want to come back to academia. And so, you know, locally, you may have problems hiring for a few years. You know, we had this problem at EPFL when I started hiring in machine learning, and you know, and everybody was saying, you know, we can't compete on salaries, and we couldn't compete on salaries. We didn't even try. But what you find out is that there are many people who don't want to be the 300th or the 400th machine learning expert at DeepMind in London. They would rather be a professor with the independence that a professor has, the opportunity to set their own research directions, the opportunity to achieve visibility and impact that you just can't get at an industrial research lab. And so, you know, I think it's very important to remember that most of our graduates are going to go to industry and are going to get hired by industry. And that is actually a good thing. We want our graduates to have jobs. We want them to have good jobs. We want them to have impact when they graduate, because it leads to a good life for them. It reflects well on the university. But that does not mean that we will not be able to hire professors, because I think that there will always be a huge difference between the freedom that you have at a university to do research and the opportunities you have in industry to do research. You know, what is more concerning to me in this area, at least perhaps locally, is that the resources available in industry are orders of magnitude better than what we can offer, even at a well-endowed university like EPFL. You know, the computational resources that you need to do state-of-the-art machine learning are extremely expensive. Universities have a great deal of difficulty sort of staying up to date, even if they're able to buy them. And the data sets are just not available in universities. And so the competition becomes a little bit skewed. that way. And that is, to me, a bigger concern than the availability of people. Because I think if you look at the sort of pool of people who go on the academic job market, it includes many, many top machine learning people who want to go to academia. And so I don't think that that's the fundamental problem. I think the resource problem is a problem. And I think the funding agencies are going to have to think about solutions for this, just as they do in other disciplines that have very heavy compute needs, like physics or chemistry. We haven't gotten there yet, but I think that we will need computational centers for machine learning, as well as physics centers like the one in Lugano in Switzerland.
Okay, thank you, James. James, good point. So before starting the last round, I just want to ask whether someone wants to add something what has been said in this second round, because I think there were some interesting points.
Well, I would like to know what you think about what Europe will need in the near future. We speak about the green transition, we speak about the digital transition. This will need a large number of well-trained young people who are green engineers, building the green technologies. All of this will have something to do with data, with digitalization, with AI, and at the same time for digitalization. So where will these large number of people who will be needed to actually do the transitions that we, the political masters, but we all are looking towards these, where will they come from? And what is your answer for this?
Is that a question to me or?
To whoever wants to answer.
Yeah, maybe Jim, maybe you and then Paul.
So I think the answer is obvious. It's the universities that have to produce them. And the students are doing it. You talked about designing a curriculum. The students are designing a curriculum even before we get there. They're taking machine learning courses, regardless of sort of what their discipline is. The largest course at EPFL by far is our master's level machine learning course. It's an excellent course. It has 500 students, which is probably twice as many as it should have, but we can't turn people away. And it's only one of many machine learning courses that are taught at the university. And the reason it's popular is because students all know that they need this skill when they go out there on the job market. They see that it's a useful skill. They see that it's being used all over the place, and they want to learn it when they are at the university. And I think it's incumbent on the university to sort of recognize that there are more than just machine learning. There are other aspects of it, as you talked about, the ethical aspects of it, the applications of it in particular domains that we should be teaching to the students, because they're the ones who are going to go working in industry. They're the ones who are going to go become the government ministers someday. And they need to understand this technology and understand when it works and when it's inappropriate. And that's our responsibility to teach them that.
Paul, you also raised your hand.
Perhaps I can just add a word on this. I was just looking up a statistic of how it is with AI PhDs in Europe compared to others. So about 60% of all AI PhDs are in the United States. 10% is in Europe. And we are losing in Europe about 25% of our AI PhDs to other countries, especially to the United States. We are also gaining about 10% who are coming from outside Europe to us. So effectively, we are losing about 15%, especially to the United States. And why are they going to the United States? Interesting what they say. The primary reason is the good professional prospect and the environment to do work. And lifestyle and culture are also important, as well as the political climate, interestingly, of the destination country. So I think it's very important to create centers like CAIML, because that's where you can show that you are having a professional environment that is attractive, where you can show that there are other elements that play a role here too, like the way of living, the culture, and those aspects that you would naturally associate. So I think we have also something to do to reverse this brain drain. And at the same time, this can also attract more people to the field.
Okay, thank you. Very good point. So maybe for the last round, I would like to try to collect very few questions from audience and the Zoom, and then we do a final round. So I'm wondering whether we have something. So Julia Neidhardt, who is monitoring the chat.
No questions so far?
No question yet. So I look in the audience. So I have one more prepared, which is maybe not so spectacular. So I was hoping that. Yeah. So in any case, let's come back. So Paul already returned to our center here, which starts now with 3 PhD students and 1 coordinator position. And we are happy about this, but of course we want to grow, not only grow person-wise, but also topic-wise, crossing the borders of these 2 faculties, also reaching out to the people who apply our techniques. I think it was mentioned in the first round that this is also a very important aspect here. And I mean, what I want to know from you is a little bit goes into 2 directions. I mean, the one is if you are aware of, or if you are involved in in a similar center, maybe you can also comment a little bit on the financial equipment you have, if this is allowed, or what size or how many people are there really in the center. And as a second question, and of course this is a kind of a trivial question, so what amount of funding would you see adequate for such a center with such a goal we have in mind? Of course, infinitely high budget, but what would you say? I mean, sometimes shouldn't. Yeah, so this would be just my question for the last round, so to say, as a take-home message for us, and also in comparison with other centers. And at this time, maybe I start with Jim this time, and then we make this round.
So this is a hard question to answer. I mean, every university is different in the way in which funding occurs. So, I would view the funding that you have currently and the people that you have as the seed for something bigger. And I would be ambitious. There's a lot of money in this field, and the money should be from the government. It should be from the usual funding sources, and it should be from industry. I mean, I don't think you should be embarrassed about going out to the industrial powers that have money and asking them to support the center as well. And I think what you need to do is you need to view the money you have as just the beginning and figure out a research program, a research direction that is appealing, and get it started with the resources you have. But do not overlook opportunities to grow it, because this is the time to do it. This is when there's interest. This is when it's in the news. This is when it's important, where you can have tremendous impact at the beginning. And so, you can't have a lot of impact if you don't have a lot of people, is my view. And so take advantage of it. Take advantage of this good start, this strong start, the people that you have in the audience, and find some exciting programs that will attract attention and will attract financial resources.
Thank you. Professor Nowotny.
Well, I agree with what Jim just said. I mean, you have an enormous potential for such a center inside a technical university, because you have a broad basis of competence that you will need. You also have relations to industry better than other universities. And, it's in the end, it's people and the atmosphere that you create around people. You have a space to be filled, a space for things to be done in common. And just to pick up on what Paul said before about language, it needs a space, but it also needs time to listen, to learn each other's language. And from personal experience, which is not directly related to AI, but it's related to interdisciplinarity. When I was a professor at ETH Zurich, I was also the director of the Collegium Helveticum. And this at that time was a small outfit in a beautiful observatory of the first professor of astronomy at ETH Zurich. And we had this wonderful space, and I could each year take in 10 different PhD students who kept being supervised by their supervisor. But they came and were working with each other and with me for 2 days the week in science and technology studies, but also learning how to communicate in interdisciplinary terms. And just to give you one example, in the beginning, I asked each of them to present their PhD work. And I asked them, choose 2 commentators, one that is closest to your own field and one that is furthest away. And the discussion was fascinating because the one who was closest, tried to act as a kind of translator and used his or her own language to translate. And the one who was furthest away was posing the most unusual, interesting questions that no one else would have posed if you are not so far away from what, the PhD was all about. And so this is how we got started in learning language and conversing. So, there are many different elements that come together, but I think you need space, you need time, and you need to build a sense of community. And if this comes together, then, it's also, sharing meals, talking to each other. Bring in, of course, your PhD supervisors, bring in the professors, but build a community around the young people who are really your greatest asset.
Yeah, thank you. Maybe Paul, what?
Yeah, thank you very much, Stefan, for that question. It's of course always hard to answer how much money do you actually need. More, it's probably the answer. But I fully agree here that this is the time and you should be ambitious. If you now look at it, the European Commission has as an aim that 20 billion a year is invested in AI in Europe. In the US, it's 16 billion. It has been argued it should go to 32 billion. China, comparable or even larger amounts. But perhaps it's not good to only look, let's say, at the European level, European funding, but perhaps also at Austria. So perhaps Austria wants to compare itself also in the field of AI to what other countries are doing and trying to see what can be done in terms of national funding. If I look at a country that is my home country, the Netherlands, they have 275 million put up for a national coalition in AI. They have put up 80 million for AI education. They have put up 95 million for a larger AI pilot and a researchers collaboration. So, the amounts are somehow crazy, isn't it? I mean, they are huge. In that sense, certainly there's a high expectation, there's scope, there's an opportunity for people that are ambitious. I fully agree also with Helga. You need to take time. It's not going to happen overnight. And perhaps that's good, because from that you get more profound insights, I would think, in this difficult field.
Okay, thank you, Paul. So for Gerhard, so Paul already suggested we now should break things down to the Austrian level, and this brings my mind up with the Austrian National Strategy for Artificial Intelligence.
Yeah.
Maybe
it got lost somewhere.
Which was a bit, now I'm being polite, disappointing, I would say, how this.
Yeah.
So maybe you can put this in some context.
Yeah.
Finally.
So I think we can agree it's about people, yes, and attracting bright minds, and so I think this is some sort of agreement. And of course, I mean, the money per se is quite not very interesting, yeah, but it helps, yeah, to some extent, yeah, to build an infrastructure and environment which is attractive, yeah. Okay, so and some countries are, there is a sharp difference, I think, between different countries. So let me, for example, if you look just to Germany, yeah, to our closest friends in Germany, in Bavaria, they are spending 360, I think 360 million euros for establishing 100 chaired professors and research groups in the field of artificial intelligence. So this is quite the competition, yeah. And so, I mean, if you say, okay, if we have to compete for the bright minds, yeah, and the bright students, I mean, there is a lot of competition. And why should one go to Vienna or to Klagenfurt when someone can earn much more money, yeah? But it's not only money, but if you can double your salary and you have a better infrastructure, which is very important, yeah, for example, in machine learning, then why should you go to Austria? Yeah. And I think, I mean, this has to be answered, yeah. But it's not only money, but it's also, if we also look to our friends in Switzerland, yeah, for example, to the financial situation of ETH, yeah, and it's quite different. But it's not. I don't say this is just the key, yeah. But somehow I think it's in order to, if we say there is a race and a tough competition, yeah, for the bright minds, yeah. Then, for example, the most important thing in Austria would be, yeah, the reputation of the Austrian universities are increased. Yeah, I mean, we have this. We have, for example, the 3 top ranking institutions. Yeah, so I mean, why don't we get, or why don't we have a program in Austria where the aim is, yeah, that almost all of the Austrian universities are in the top 100. I'm not talking about the top 10, yeah, just talking about the 100. Yeah, and this requires some resources, and I don't see these resources. Yeah, I mean, I think given the resources we have in Austria, for the universities, we do a tremendous job. Yeah, tremendous job. Yeah, but I think the Austrian government sometimes must acknowledge that research is important and research is our future, and we need enough resources for research on a general level, and particular in machine learning and artificial intelligence.
Okay, thank you, Gerhard. So I think this was as a final statement. We can let this stand as it is. Thanks a lot, Paul. Thanks a lot, Jim, for being here via Zoom. It was, at least for me, a very, very interesting discussion with a lot of input and things to bear in mind now when starting with the center. And I hope also that we can come back to you at any time if we have some question, or if we have to make a hard decision what to do next. So thanks again. And I think we now come to the closing remarks, and Clemens takes over. Thanks.
Well, can I?
Sure, please.
Sorry. No, I just wanted to mention digital humanism as you know, something that other centers do not have, and because you need something that is not just attractive for the reasons that we all agree upon, but you know, what is the sort of extra that and I think if we take this seriously, I think that the center here at the Technical University, by linking up to digital humanism, could really become the kind of center we would like it to become. And in my experience, this may sound a bit harsh, but in my experience, if you have good ideas and good people, money will follow.
Thank you very much.
All right, we have one last slide. All right, so thank you very much for this thoughtful discussion and the many interesting points that will turn out to be useful to us. Our opening event is coming to an end, and we have some closing remarks for you. I will talk about the first few points here, and then I'll hand over to Stefan. We have our website up and running. It's at kemel.org, so please have a look there, and we will continually update it with the latest information on upcoming events and activities. We would just like to point out some immediate events and activities that we are organizing in the coming months. As you can imagine, we are hard at work, and this is what we have planned so far. In March, we will have a talk by a renowned international speaker, which will be just the first in a series of such talks. We will welcome a guest professor in digital humanism, Edward A. Lee from UC Berkeley in the US, in cooperation with the Institute for Human Sciences, IWM. In May to June, I co-organize a thematic program on uncertainty quantification and machine learning at the Erwin Schrödinger Institute here in Vienna. So there will be topics in machine learning that will be discussed. And I'm happy to point out that Stefan is organizing a conference. He will tell you more about it now. So at this point, I would like to thank you for joining us today, and I'll hand over to Stefan.
So thank you, Clement. So it's now my turn for the final words. So in fact, we will have the ECHI conference 2020 in Vienna in July, so which is the largest international conference in the AI area. And Magdalena Ortiz and I act as local chair, but we are very happy that we could, so to say, work together. We have a large local arrangement committee where we have the AI community in Austria helping us in different aspects also. Gerhard is on board here, so that's also maybe a boost for the Austrian AI community, where we are looking forward very much to in July. So final words are words where we want to say thank you. We want to thank all the people who made this center possible in the face of the design, in the face of trying to shape how it works. I want to just make one particular thank you to our former dean, Hannes Wertner, who also always supported us in coming up with this center. I would like to thank all the speakers today, all the panelists for joining us. I would like to thank, of course, the audience for being with us this evening. And so now I look at my paper so that I must not forget someone. Thanks also to our media partner, Wiener Zeitung, who promoted this event today. And last but not least, I also would like to thank the technical and administrative staff. Without you, this would be impossible. It's a very complicated setup, but everything worked smoothly. Thank you very much. So thank you for joining us. See you soon, hopefully in person, some event of the center. Thank you very much and good night.
Really?